Okay. Uh, so in today's class, we starts with the mathematical expectation of a function in bivariate distribution, right? So here we'll go through the first. In today's our regular classes, we saw that what do you mean by bivariate distribution? That is nothing but two-dimensional random variable. The distribution function or the probability mass functions or probability density functions which has two random variables, right? So now we are going to discuss the expected value of any function g of xy. So how to find out this? This is nothing but double summation. Why double summation? Here we have two random variables, one I running from 1 to m and one more j running from 1 to n. Right? So now here g of xy is there. Instead of x, what we have? Uh, g of xi comma yj into probability of I comma j. So this is nothing but the mathematical expectation of a function of a bivariate distribution, right? For continuous case, same. This is for discrete case. Then for continuous case, the expected value of any function, that is double integration minus infinity to infinity minus infinity to infinity g of x comma y. Then here we have f of that is joint probability density function or joint probability mass function with respect to dx and dy, right? So this is whenever x and sorry not is right. So first formula for discrete case, and this is for continuous case, right? So this is what the definition of the mathematical expectation of a bivariate distribution, right? So say for example, just you put instead of this g of x comma y, just for our convenient purpose, suppose I will put, right? So g of xy is equal to x plus y. So now expected value of x plus y is nothing but what we have, some double summation, one I running from 1 to m and one j running from 1 to n. Here we have xi plus yj into pij, right? Say for example, suppose we have g of x comma y is equal to x square into y, then expected value of x square into y is equal to double summation, right? So I running from 1 to m and j running from 1 to n. So here what we have, x square, xi square, then yj into pij, right? So like this, instead of g of x, we have any function. Instead of g of x, we have any function, right? So this is nothing but the expected value of bivariate distribution. For this instant, we have one example here. Example, for the following, for the following probability distribution of, for the following probability distribution of x comma y, compute the first one, expected value of 2x plus 3y, then second, expected value of x square into y. So they given one two-dimensional distribution here. So this is x and y. So y takes the values 1, 2, and 3. So x takes the value -1, 0, then 1. With probabilities are also mentioned. This is 0.15, 0.1, 0.2, 0.05, 0.05, 0.05, 0.15, this is 0.2, and this is 0.05, right? So here our aim is to find out expected value of uh, 2x plus 3y, right? So here g of x is nothing but what? See here. See, in first case, our g of x comma y is nothing but 2x plus 3y, right? So now we are going to find out expected value of 2x plus 3y. So for this, so expected value of 2x plus 3y equal to, so by the definition of bivariate expectation, so I running from here 1 to m and j running from 1 to n. Instead of this g of xy, what we have? 2x plus 3y into probability or at I comma j, right? So this is what the formula to calculate bivariate expectation, right? So this is equal to, see here, first we'll consider this x equal to -1 and for various values of y, right? So 2 into -1 plus 3 into 1, right? Y equal to 1. So 3 into 1, right? So for this Pij means what we took? I equal to -1 and j equal to 1. So I -1 and j 1. So common probability is this one. This is 0.15. Clear? Plus. Now our x value should be -1 only. Now we go for y equal to 2. So 2 into -1 plus 3. 3 is there here. This will be 3. Y is 2. So now into 2. So its probability is 0.1 plus 2 into -1 plus 3 into 3, right? So here y value is 3. Its probability is 0.2. Its probability is 0.2, right? So here x equal to -1 completed for various values of y. So now we'll go for x equal to 0 plus 2 into 0 plus 3 into y equal to 1, and its probability is 0.05 plus 2 into 0 plus 3 into 2. Its probability is 0.5 plus 2 into 0 plus 3 into 3. Why this is 3? Because of this 3y. Its probability is 0.05 plus. Now our x value is 1. So 2 into 1 plus 3 into y is also 1 into its probability is 0.15 plus x value is 1 plus y value is 2 and its probability is 0.2 plus x value is 1, y value 3 and its probability is 0.05, right? So in this way we need to simplify this calculation or this equation, whatever you called, right? Clear? So after solving, we'll get, see here, by each solution, we'll get expected value of 2x plus 3y is nothing but 0.75. Later you can verify this value is 5.75 we will get. Right. So in this way, we need to find out the expectation of two-dimensional or expectation of bivariate distribution case. Now we go for this is our first answer. Now we go for second one, that is expected value of x square into y. So second what we have, expected value of x square into y. Same, the formula remains same, that is nothing but summation I running from 1 to m and j running from 1 to n. Instead of g of x comma y, what we have? The function x square into y, then pij. Right? So here what we'll do? Here we'll consider the same that table. So first x is -1 there. So -1 square and y is 1 and its probability is 0.15 plus x is -1 square, y is 2 and its probability is 0.1 plus x is -1, it's the square, plus y is 3 and its probability is 0.2. Right? So now plus, we'll consider x equal to 0 now. Right? So 0 square 1 and its probability is 0.05 plus 0 square into 2 into 0.05 plus 0 square into 3 into its probability is also 0.05 plus now x equal to 1 and for various values of y, 1 square into 1 0.15 plus 2 square into 2, sorry, it is 1 square not 2 square, x value is 1 here, 1 square into 2 0.2 plus 1 square into 3 into 0.05. After some simplification, you will get this answer. You can try. So expected value of x square into y. So here expected value of x square into y is nothing but 1.65. Right? So just to multiply, square, multiply, square, multiply, again add. Like this, suppose you do calculation, you will get 1.65. Right? So this is what some few example to understand the basic concept of bivariate mathematical expectation. Clear? So I hope this concept, I mean this example is clear. Now we go for some theorems. Theorems on expectations. Theorems on expectations. Right? So here we have the theorems in the form of statements and proofs. So first I will write the statement. Let x and y be two discrete random variables. Two discrete random variables. Random variables. Then expected value of x plus y is equal to expected value of x plus expected value of y. Right? So whenever x and y are discrete random variables, there we are going to prove expected value of x plus expected value of y. Right? So this theorem is also called as addition theorem of expectation. Right? So this is also called as addition theorem of expectation, right? So in exam, they may ask state and prove addition theorem of expectation for a discrete case. or state and prove addition theorem of expectation for continuous case. Like this they may ask, right? So here what do we consider? Here x and y are discrete random variables for that. So let us consider Pij. Pij will be joint probability mass function, right? Let Pij will be the joint probability mass function. Already you know what do you mean by the joint probability mass function, right? So now consider the left hand side of this, that is expected value of x plus y is equal to, right? By the definition of bivariate mathematical expectation, one running from, I running from 1 to m and j running from 1 to n. Instead of g of x, what we have? We have x plus y. That is nothing but xi plus yj, then Pij as it is, right? So here, so summation I running from 1 to m and j running from 1 to n, right? So here what we'll do? We'll do this Pij, we'll need to multiply this Pij inside, right? So when you multiply this Pij inside, so this will become xi Pij, right? Addition is there, plus then after that yj into Pij, right? So here whatever we have this summation, double summation, it will be applicable for both the cases, equal to, right? So now we will apply this double summation for each each calculate values here. So first double summation apply for this. So double summation I running from 1 to m and j running from 1 to n, xi Pij, plus now this double summation applicable to for this second term. So double summation I running from 1 to m, j running from 1 to n, yj Pij, right? So here I running for only x wherever, this summation runs for wherever I only we have. So that is nothing but summation I running from 1 to m xi, right? And here summation j running from 1 to n Pij, plus summation j running from 1 to n yj, summation I running from 1 to m Pij, right? So here this is as it is, summation I running from 1 to m xi, right? So this term I will treat as one new term, that is nothing but p, j is running here, so I will take p I dot, right? So dot means it varies, plus summation j running from 1 to n yj, so this is p dot j, right? So where pi dot and p dot j are marginal probabilities, marginal probabilities, right? So here now I will go back to this equation. We'll go back to this equation, right? So just see here, I'm sorry for this interpretation. Here, this is nothing but expected value of x definition, and this is nothing but expected value of y definition, right? So here, this is summation I running from 1 to m xi pi dot is nothing but expected value of x, and summation j running from 1 to n yj p dot j is nothing but expected value of y. So earlier left hand side what we have? We have expected value of xy, which is equal to expected value of x plus expected value of y. So this is nothing but proof of this theorem, right? So this theorem is called as addition theorem of expectation, and here not only xy, in generally, if x1, x2, x3 and so on up to xn are n discrete random variables, or n discrete random variables, then expected value of x1 plus x2 plus x3 and so on up to xn is equal to sum of their individual expectation. That is nothing but sum of their individual expectation, and then their sum, right? And so on up to expected value of xn. This is exist for in generally. How? This is nothing but generalization of addition theorem of expectation. Right? This is nothing but generalization of addition theorem of expectation. Clear? So I hope it's clear, right? Now we go for multiplication theorem of addition. One more theorem we have. Theorem, this is called as multiplication theorem of expectation. Multiplication theorem of expectation, right? So now we go for first statement, then we go for the proof. Statement. Let x and y be two independent discrete random variables, then expected value of xy is equal to expected value of x into expected value of y. Expected value of xy is equal to expected value of x into expected value of y. So here in the statement of this theorem, multiplication theorem, the statement is very clear. Let x and y are, this word is important, this is independent discrete random variables, right? If they are not independent, this theorem does not exist. Very clear, right? If it is not independent, this theorem does not exist. If one only if is this theorem has to be applicable, means those two variables are independent. That is must, right? So here proof. So here expected value of xy is equal to summation I running from 1 to m and j running from 1 to n. Instead of g of xy, what we have here? Xi into yj, then into probability of, this is nothing but our definition, right? So expected value of xy is equal to double summation I running from 1 to m and j running from 1 to n xi into yj. So here this probability pij, right, it will be multiplied like this. Pi dot means individual probability, p dot j. Why? Because x and y are x and y are independent, right? So whenever x and y are independent, so that is nothing but our what is that? multiplication theorem of independent variables, right? So probability of A intersection B, probability of A into probability of B. This is called multiplication theorem of independent observation. This is P of A is nothing but Pi dot, and P of B is nothing but P dot J, like that, right? So here, this is individual multiplication. So now we'll take like this summation I running from 1 to m xi and pi dot into summation j running from 1 to n yj p dot j. So this is nothing but our expected value of x into this is nothing but our expected value of y. So left hand side we have expected value of xy, right? So this is proof, right? So this is nothing but the multiplication theorem of expectations, right? Is it clear? So I hope it's clear. This is also okay. This is called multiplication theorem of the expectations, right? So it's generalizations. How we have the generalization of our addition theorem of expectation. So in generally, if x1, x2, x3, and so on up to xn are n independent random variables, are n independent random variables, then expectation of x1 into x2 into x3 and so on up to into xn is equal to product of their individual expectation. That is nothing but expectation of x1 into expected value of x2 into expected value of x3 into and so on up to into expected value of xn, right? So this is exist in generally, right? So this is also called as generalization of multiplication theorem of expectation, right? So then there is one important note point, right, in this particularly. So converse of this theorem does not true. So then what is the meaning of converse of this theorem? Means product of this individual expectation, product of their individual expectation is not equal to expectation of uh, product of random variables, right? So this is not exist, or particularly this is not true in generally. Clear? So now we go for one example. Now we go for one example of this kind. Example. Let x and y have the following joint probability mass function, right? In the form of table here we have, not in the form of function, right? So here we need to draw a table first. So here y values -1, 0, 1. Then x values 0, 1, 2, right? So and they given the sum of probabilities also, that is nothing but our marginal probabilities are also mentioned here. Pi dot and P dot J. So this is 0, 1 by 6, 0. Summation of this 0 plus 1 by 6 plus 0, this is 1 by 6. 1 by 6, 0, 1 by 6. 1 by 6 plus 1 by 6, 2 by 6, that is nothing but 1 by 3. So it's 0, 1 by 2, 0. 0 plus 1 by 2 plus 0. This is 1 by 2. Next, like this summation. 0 plus 1 by 6 plus 0, 1 by 6. This is 2 by 3. And this is 1 by 6. Right? So now, we are going to find out the expected value of, find first one, expected value of xy, second, expected value of x, third, expected value of y. Right? We are going to find out these values. Now, to find out expected value of xy, what is the formula? To find out expected value of xy, the formula is double summation because it is bivariate case. To find out expected value of xy, so double summation, I running from 1 to m and j running from 1 to n, xy, pi, j, right? So this is nothing but, first we take x equal to 0, right? So 0, then y minus 1 and its probability is 0, plus x is 0, y is also 0 and its probability is 1 by 6, plus x0 and y is 1. x0, y is 1, but its probability is 0, plus. Now we go for x equal to 1. So x1, here multiplication is there, simply we are taking multiplication. Then minus 1, its probability is 1 by 6, plus x0, y0 and its probability is also 0, plus x is 1, y is 1, then its probability is 1 by 6, plus go for x equal to 2. X is 2, y is minus 1 and its probability is 0, plus x is 2, y is 0 and its probability is 1 by 2. Next, plus x is 2, y is 1 and its probability is 0. After solving this is nothing but our expected value of xy. So expected value of xy, by simplification, we will get, see what we'll get here, 0 is there, so this entire term is 0, plus here 0, entire term is 0, here is 0, plus 0, plus here 1 into minus 1, that is minus 1, minus 1 into 1 by 6, that is minus 1 by 6, plus entire term is 0, plus 1 by 6, plus 0 is here, 0, here 0, plus 0, plus 0, right? So what we get, expected value of xy is equal to minus 1 by 6 plus 1 by 6. So minus 1 by 6 plus 1 by 6, 0, right? Now we need to find out expected value of x. So formula is very simple. Expected value of x is summation I running from 1 to m xi pi dot, right? So this is nothing but by that table, right? So x equal to 0 and its probability is 1 by 6. Yeah, whenever x is 1, its probability is 1 by 3. Whenever x is 2, its probability is 1 by 2, right? So it is 0 into 1 by 6 plus 1 into 1 by 3 plus 2 into 1 by 2. So this is nothing but 0 plus 1 by 3 plus 1. So the answer is 4 by 3. Now we need to find expected value of y. That is summation j running from 1 to n yj p dot j, which is equal to, see what are the values of y? Minus 1, its probability is 1 by 6, 0, its probability 2 by 3, 1, probability 1 by 6. Is it clear? To find out individual expectation, whenever the data is distributed two-dimensionally, to find out individual expectation, we required marginal probabilities. Is it clear? The main application of marginal probability is to find out the individual expectation whenever your data is distributed two-dimensionally. It means that whenever your data is involved two random variables, then at that time to find out individual expectation, we required marginal values or marginal probabilities, right? So minus 1 into 1 by 6 plus 0 into 2 by 3 plus 1 into 1 by 6. Right? So here minus 1 into 1 by 6 plus 0 into 2 by 3 plus 1 into 1 by 6. So this is nothing but what? Minus 1 by 6 plus 1 by 6, which is also 0. Right? So here conclusion, xy, expected value of xy is 0, expected value of x is 4 by 3, and expected value of y is 0. Is it clear? Is it clear or not? So this is nothing but some one example regarding the whatever we discussed, the concept of bivariate case, right? So whatever I discussed up to here, this is nothing but bivariate expectation, especially discrete case, right? Is it clear? So now I will stop the class here because there is some disturbance in a particular locality. Tomorrow I will take the mathematical expectation for bivariate case for continuous case in that, right? So just quick revision of the today's class. Just see here mathematical expectation of a function in a bivariate case, right? So we discussed only upon only this formula, that is double summation g of xy pij, right? So here I took some various values of g of x. Next, here we solve one example how to solve or how to find out expectation of bivariate case, right? And this is addition theorem of expectation. Next is proof and generalization of addition theorem. This is called multiplication theorem of expectation, right? The thing is, when to apply, you will be very clear. If x and y are dependent, we can't apply multiplication theorem, but we can apply addition theorem, right? So while applying multiplication theorem, it is only matters about the dependency, right? Then this is a proof of the multiplication theorem, then generalization of multiplication theorem, and we solved one example, right?